The exam on Monday, be here, 10:30, be awake, bring some pencils, bring some coffee, whatever you need to be on the ball, on form, and let's see what we can do. We started off as very sort of naive general chemists who came in knowing how to use a calculator and knew all about significant figures, and we haven't seen a single significant figure. It's been great. And then we started talking about the sort of progression of organic chemistry and how I hope at the end of the 2 semesters of this stuff, you can go back and see general chemistry in a different light and hopefully understand a bit more, and then progress into the bigger subjects like polymer chemistry or biochemistry and appreciate how molecules come together and how they react. So we're going to very quickly skim through a bunch of slides here just to show you where we've gone. I'm going to drop some heavy hints as to what's going to show up on Monday. My job is here to get you ready for the second semester because everybody has to take it, and I need to know that you know certain things. So on day 1 of the next semester, we come in and we're ready to go because we've already done this stuff in the first term. Organic synthesis is a massive subject. It's gotten way more complicated in recent years because of all the technology we've developed to build very complex molecules. But the fundamentals are the same. If you look at that very complex molecule, you should be able now to pull out sp2 carbons. You should be able to tell me what's flat, what's tetrahedral. You should understand shape, and most of you can. Those bond angles stay the same next term. We do a lot of sp2 chemistry next term with carbonyls and stuff like that, but it's still trigonal planar, it's still flat, potentially it's still prochiral. All those words still come into the game. We talked about properties in lab. Lab is important. If you haven't got your lab finished, do it now, because those points are important, and you must pass the lab to get a grade for the class. Those properties, again, next term, we will develop new ideas, similar mechanisms, develop spectroscopic ideas to actually use this stuff and to solve problems. So this is becoming hopefully tied together more in the second term. Functional groups. You must know what the functional groups are. You must know what these things are for Monday and for next semester. So know what an aldehyde is, know what a ketone is. We have spent time using those terms all the way through. They should be in there by now. Go back and look at these charts and make sure that you're happy with these functional groups. We're going to expand on them next term, but certainly alcohols, alkynes, alkenes, halides, they're all still going to be useful in 3720. You should be able to look at a big molecule like this. When we showed this on the first day, some people went, oh no, and some people went, wow, cool, there's a lot going on there. Anti-cancer compound, very complicated, supplied from a natural source. You should, at this stage of the game, be able to look at that from different perspectives. You should be able to tell me about shape. You should be able to tell me about hybridization patterns. You should be able to tell me about reactivity. We have ethers in there. We have some alcohols in there. We have some carbonyls in there. You should have some idea of what these things can do by now. And also, we have lots of wedges and dashes, so we should be able to do some RNS configuration type material. All right? So there's stuff you've picked up, and hopefully you're feeling as if you've picked up some skills by now. Thinking about the second term, we have been trying to work our way through these mechanisms in a systematic way so that we build up the complexity and the utility throughout the term. And a lot of it was based on lone pairs. If you recognize where lone pairs are in a molecule, you understand a lot about that system. Next term, we'll concentrate on oxygen and nitrogen, how they react and bond with carbon to make bigger molecules. But again, this idea of electron counts, most atoms want to have 8 electrons. If they're missing some electrons, they tend to be reactive. Some electrons can be shared, like lone pairs. And this chart here is showing you the possibilities for nitrogen. And we also have that for oxygen and carbon. So understand that those basic principles now will be tested on Monday. A quite detailed exam. You should be done in 2 hours, no problem. But certainly it's a test to make sure that you're ready for the second term. Resonance. Everybody who's passing the class needs to be understanding resonance, should be comfortable with drawing structures, even on things you haven't seen before. Simply thinking about the needs here, thinking about the picture on the left. The second term is heavily involved with these compounds here, the carbonyls, and those carbonyls are very important. They're also very polar. And the chemistry here will be involved, nucleophiles attacking this carbon. Why? Because it's so positive, and that can be described by these 2 resonance structures. Understand that the molecule is not this, and it's not this, it's somewhere in between, and we have practice drawing resonance hybrids, so be ready for that kind of thing on Monday. Down here at the bottom, we have a similar situation with an ether, where we have a positive charge next to an O, and over here on the right, we've pushed some electrons around to make this, this structure. Which of these 2 structures are better, the left or the right? The one on the right, why? Remember these rules from way back? Octet rule, right? Octet rule. On the right-hand picture, all the atoms have 8 electrons, even if oxygen is positive, it doesn't matter. It's very much like H3O+, it's helping out, it's stabilizing the system. So be ready for resonance. Certainly be ready for acids and bases. If you've forgotten your pKa's, spend all Saturday and Sunday. You know, Ohio State are out to the championship games now, so, you know, might as well just stay home, do your pKa's, nothing else happening in the world, learn these pKa's. learn the table, learn the basics of the chemistry. There's a full page there of 20 points, 10% of the grade on Monday is acid-base chemistry. Give me the products of these acid-base reactions. Tell me where the equilibrium lies. Very similar stuff, but again, setting up the second term so we can start to use that material. We had some basic ideas from the book. They suggested looking at the atom that's involved. Is it oxygen? Is it nitrogen? Is it sulfur? What role does that play in terms of electronegativity? Resonance, can you stabilize a negative charge? If so, that will be a weaker conjugate base leading to a stronger acid. Induction was all about having things like CF3 groups or CCl3 groups that then pulled electrons away from a negative charge. And the orbital was all about hybridization, right? And we've seen that more recently. sp hybrid carbons are more electronegative than sp2. That's why the CH bond on an alkyne is more acidic than an alkene, and then more acidic again than an alkane. So those have all come together in the past few weeks. Know this table, not just for now, but for next term. All right. What the problem with the second term is, we started out this semester with 144 people, and this room was almost full. It was pretty busy, and now we're down to probably 90 we'll get through, maybe 85 we'll get through. 96 enrolled for next semester. Of those 96, typically, you're looking at maybe 60 people get through. And it's because they slacked off over the break and they didn't come back in ready to go. So know these numbers, not just for now, but for next term, so that we can call on them very quickly. Understand the basics behind these numbers, and then we can start to use them to do more complicated mechanisms, but just building on what we know. Confirmation analysis, my favorite. It's all my favorite, let's face it. This stuff is all about bonds rotating and all about the consequences of that, groups getting in each other's way, starting to see some ideas of steric problems and torsional strain and things like that. There is a question on Monday of this nature. Okay, you've got to go back again and look at the Newman depictions. Think about the interactions in a Newman depiction. Which is better, which is worse? Thinking about thinking about gauche, thinking about eclipse type of conformations. Be very careful. This is a nomenclature question too, so there are some points in there for getting the molecule right and getting the shapes right. So think about least stable, think about most stable, and just review this stuff because most people who are left are okay with this. We'll also do some boats and some chairs and things. These graphs, again, second term, we'll use them. We'll start to understand more about kinetics versus thermodynamics in terms of reactivity. We'll talk about stability versus instability again. Know how to draw these pictures. Understand the basics of why things are more stable and less stable. If we look at the chair down here at the bottom left, it's the best situation because all the atoms are sp3 hybridized, and in that chair conformation, they can all be tetrahedral without any eclipsing. Okay? As you start to go to half chairs and things like that, you start to get eclipsing. That's why it goes higher. We will see a question like this on Monday. It's just a good way to make sure that you've remembered, you've gone back and you've thought about this. If you didn't do so well on the first time, you can do better now, get more points. Think about cyclohexanes. Think about having big groups in the equatorial position versus the axial position. Think about why that's important. Think about if you have 2 or 3 groups, the largest group will win. It will want to be equatorial. Everything else has to go where it's told. So we'll have some comparison here on Monday, 10, 12 points, whatever, in which you have to tell me which of the shapes are more stable in the system, and then go between the cis and the trans and tell me which is more stable between those two, based on these diaxial interactions. So stuff you've seen before, just to make sure we've still got it. We then went off into stereochemistry. We talked about all these ideas of R and S and all this idea of configuration. And you've got to understand the difference between configuration and conformation. This is something that's worth talking about for a minute here. Configuration is set. You are cis or you are trans. And you can't go between the two of them. You are R or you are S. And you can't go between the two of them. Conformation is like standing up or sitting down. You're changing your shape. It's a boat versus a half boat. It's a chair versus a half chair. So understand that. Configuration is set. Conformation is flexible. We'll talk about, we have talked about in the past these ideas up here, and words that we have used to describe the different isomers. In this molecule at the top left, I have 1R, 2R, 3S, and then next to it I have 1S, 2S, 3R. What is the word to describe the relationship there? They're enantiomers, absolutely. And then you move across, and what you're doing here with 3 stereocenters is trying to maximize the number of isomers you can get. And the idea would be 2 to the n is the maximum you can get, so 2 to the 3 would be 8. That's why you've got 8 pictures there. Really, that is just all the combinations you can put together that are different for wedges and dashes in that system. Well, these are not enantiomers, are they? This one over here is not the mirror image of that. So what's the word that describes those two? Diastereomer, absolutely. Be very careful with those things. Sometimes we get symmetry. What's that called? If you get symmetry and the thing that you can cut it in half, meso. Watch out for those things. Mechanisms. Everybody loves them. People rave about them, right? There are lots of them. We've done a certain number. We've got many more to go. An awful lot of you, certainly those of you in the biological end of things, and the engineers now can take biochem, right? To avoid PChem 2 or something like that. Yeah, like that. Mechanisms are going to lead to biochem. They're going to be very important for understanding biosynthesis. So we did a lot of these. We start off by trying to understand the basic principles. Why do systems do carbocations in some instances? Why do other systems do radicals? And the idea being the bond strengths, what's allowed, what's the polarity of the mixture, what does that lead to? So we had two very simple but quite different possibilities here. Heterolytic was the vast majority of the mechanisms this term, where bonds broke, where two electrons got pushed around. And then homolytic was towards the end in chapter 11, I think it was, where we did the radical chemistry. And this was based on breaking weak bonds between things like bromine and bromine, oxygen and oxygen. There was a consistency there. And you now should be able to tell what's going to happen when. Polar systems typically will do polar mechanisms, and the radical mechanisms are ones that you can pick out because you have weak bonds in there. So the vast majority of next term is all about two electrons. It's all heterolytic. But you've got to understand and remember the homolytic stuff. So we did some reaction profiles. There's a question on there on Monday. Draw me a reaction profile for this process. Here's the starter material, here's the reagent, here's the product. What happened? And again, the point of doing this is to hopefully get you thinking that for a chemist, this type of picture parallels, and in fact is the same thing as a mechanism. It shows you the energetic changes. And you should be able to go backwards and forwards between the two pictures mechanistically with all the arrows and these things with the curves and understand the differences. So for example, why am I going uphill here? Okay, because I'm going to something unstable. It's exothermic. No, it's not, it's endothermic. Why is this thing so high? It's missing a pair of electrons. It's got 6 electrons. Why is it in a valley, not at the top of a hill? Because at the top of the hill you have transition states, which we can't really see. You can measure a carbocation, you can measure the starter materials, you can see them, but you can't really measure a transition state. So at the top of this hill we have the transition states, and down here is in the valley is the intermediate. And that intermediate won't last very long because it's reactive, it's missing a pair of electrons. It will react with something else like a nucleophile or a base and give you a stable product. How many steps in this reaction? 2, which is the slower step, the first or the second. So that's rate determining, right? Is it unimolecular or bimolecular in that first step? Unimolecular. No. Right? Because this thing is breaking apart, the chloride is not needed until the second step. If you add in more nucleophile, if you add in more chloride, does it go faster or stay the same? Stays the same because that chloride is not involved in the slow step. Important ideas. Well, the book, one of the things I like about the book is it tries its best to do things systematically and try to demystify this stuff. You could teach this stuff and using a different textbook and just go at it for 15 weeks and just hammer mechanism after mechanism after mechanism. But unless you have context, it doesn't really sink in. And you want to learn this stuff so you can take it with you. 4 different types of arrows to describe the heterolytic processes. In the first one at the top left, we've got a nucleophile attacking an electrophile. It should be in there by now. Electrophiles are positive things or delta positive. So alkyl bromides are electrophiles. Carbocations are electrophiles. Nucleophiles, anything with a lone pair. And that got complicated because anything with a lone pair is also what? A base. Because any nucleophile can be a base and any base can be a nucleophile. And that's where some of the later stuff got complicated. But simply here, if you're adding a nucleophile to the electrophile by forming one new bond, that therefore is nucleophilic attack. It's not proton transfer, it's nucleophilic attack. A lot of the mechanisms we saw this term, the E1, the SN1 for example, involved a leaving group breaking off at some point. So a electronegative element, such as a halogen, was able to break away, take a pair of electrons with it, and form a stable anion. And also form this intermediate carbocation, which then gets trapped and goes someplace else. So that certainly, we should recognize that. And on Monday, if you've got a bromine in a molecule, what's it going to do for the most part? So let's make it leave, please. Okay, make it leave. Down here at the bottom, next term, a lot of catalysis. We're going to get into catalysis heading towards biochem. This idea that you can speed things up by adding protons or by adding base, and this is an event such as this, which is a proton transfer at the bottom left. You simply have a pair of electrons from the oxygen going after a proton. Very, very, very reactive acid, very acidic material, and so this should be a favorable process. And over here on the right-hand side, we have a protonated species. Next term, there'll be a lot to say about that in terms of its reactivity. That process there, that proton transfer, will speed up the subsequent chemistry by adding that acid. So the proton transfer, if it involves an H, you have to be careful here. There are 2 processes we've seen that involve H being moved around. First off, the proton transfer. If you're attacking positive H, that's a proton transfer. The other situation was a hydride shift. When you had a carbocation, maybe a secondary system, and it could rearrange and give you a tertiary system. That H that could possibly move is not H plus, right? You think about it. Plus over here, and it's trying to move across. It's not a plus going to a plus. It's taking its pair of electrons with it. So it's a different thing again. That is not a proton transfer. Down at the bottom here, rearrangements. There'll be a rearrangement there on Monday. Got to make sure we're okay with this stuff. There will definitely be a rearrangement of some sort there on Monday. And the driving force for this is usually quite obvious. If you had a 4-membered ring and a positive charge next door, what do you think it will do? It'll open up to become a 5-membered ring because it wants to get rid of strain. If you had a secondary carbocation here and it could migrate to someplace else, where's it more likely to go? Tertiary. Logical ideas based on stability. So look at those arrows again. I will start off 3720 in January by summarizing this again so that we're up to speed. In terms of the ideas behind mechanisms, we try, and I think it's sinking in for some people, we try to do this logically. We try to give you some of the examples, the sort of case studies that give you the typical types of systems, and then we build off of that. So we started out very early on in the mechanism chapter talking about concerted versus stepwise. And as we built in the stereochemistry, we can start to see the clues. The clues, the actual stereochemical outcomes, give you an awful lot of idea about the mechanism. So if you get a system which is both things have added on the same face, what was that typically? Concerted or stepwise? It was concerted, wasn't it? The H2, the addition of borane, stuff like that. And if you got systems which had maybe squiggles all over the place, what does that tell you? Stepwise. You've got carbocations or you've got radicals in which things happen in steps. So be careful here. The concerted types of mechanisms you could write on one page. You've got the H2 addition, you've got the HB, the parachute addition. You've got the addition of ozone, for example, that was concerted. They're all the same type of idea giving you a syn outcome. Stepwise, there were more of them. Stepwise, we had Markovnikov addition with carbocations. We had halogenation, we had bromination with the Br2, we had hydrohalogenation with HX, we had hydration with acid, H3O+. They were all stepwise through carbocations, and those then were more complicated. But they all involved carbocations. And what's the problem with the carbocation? They can rearrange, right? So if we can, in a synthetic sense, towards the end of the talk here, we'll prefer to do the, let's say the E2 versus the E1, because the E1 involves carbocations, the E2 does not, and the E2 is easier to put the molecule, it's easier to make the molecule you want because you can direct things the way you want to. We're not going to see any calculations, obviously, on Monday. The chemical engineers can put the calculators away for a while. This now is important, not just for my class, but for later, understanding where these terms come from, understanding what the 2 in SN2 means. So the substitution here is bimolecular, which means if I dump in more nucleophile, what happens? It gets faster. And why does it get faster? We're okay with saying that, but why does it get faster? What's the physical background? There are more things in there that can collide with each other. You've got more chance of collisions, and that will speed things up. So in the SN2, for example, down here, when we talk about reaction kinetics, we're asking that same question. What experiment allows me to decide, is it unimolecular, is it bimolecular? And that's typically the right answer. On Monday, be expected to differentiate between one and the other. Here's some evidence, here's some clues, or here are some clues. What's going on? What mechanism is this, and how can you tell? Think about reaction profiles again in terms of rates of reaction. We should be happy with why the steric environment has something to say about this. If you start to add bulk to a system, you start to shut down certain mechanisms. So you had a tertiary system. Can it do SN2? No, because it's too crowded. It should be in there. But a tertiary system can go someplace else, right? It can break apart into carbocations, and then you're okay because you've got something that's stabilized by Haldeman, certainly is, and hyperconjugation is. Your last chance. Don't get it wrong. Don't be nervous. Come on, man, spit it out. Something like that, yes. So the molecules go to the same place ultimately, but by different routes, depending upon the environments, depending upon the conditions, and things like hyperconjugation or steric environment. So those rates of reactions, I think, are fairly obvious right now. More of that next term. In terms of carbocations, there's your hyperconjugation idea. There are pictures trying to show this. The more neighbors you have, the better. The more stabilized you feel because of the electron density from those neighbors will help out. We don't draw methyl carbocations. We don't need to. We don't draw primary carbocations because we can go other places. But secondary certainly are okay and tertiary are good. And you've done that in the lab yourselves. You actually did that with the T-pentyl chloride. You ran that at room temperature, right? That was the one in the separatory funnel that you shook, and there's enough energy, enough heat in your hand to make that work and give you a carbocation. So they can be formed even at room temperature. We've moved on into eliminations. In the earlier chapter, we did all sp3 chemistry, where we swapped sp3 for sp3, but then we expanded things by looking at the idea of introducing an alkene. An awful lot of natural compounds contain alkenes, so we need to have methods to do this, and they're very, very useful materials, for example, for polymers. So ways to do this again. We broke this down earlier into concerted versus stepwise. Same idea in this chapter. We tried to keep it consistent. We have, at the top, a system in which a base is going after a proton at the beta position, and a leaving group is breaking off. Is that unimolecular or bimolecular? That's bimolecular, right? That's the E2. That's a concerted pathway. And then we had issues of regioselectivity and sometimes stereoselectivity. We'll mention that in a second. Down at the bottom, if you don't have a strong base, if you have the possibility of this breaking off on its own, maybe an H2O plus can break off, like in the E1 process, you can end up again with elimination chemistry. And there were arguments back there about all sorts of stuff in terms of how do you make this work. You heat things up to benefit delta S and also possibly to remove the product by distillation. Okay, Marissa, you're looking a bit sort of, okay. Regioselectivity. Again, there's a question there on Monday, I don't know, maybe 9 points. Define these things. Tell me what these things are. Give me an example of what these things are. Not giving anything away here, just saying this is what I want you to know for next term, so I can get started. We've got here a system in which we can change the outcome dependent upon the base. You go back and look at this now, it's a bit mysterious back then, but we've been using Cottbus for months now, right? This stuff now makes sense. If you want to make the less substituted alkene, you need to do a Hofmann elimination. If you want to make the more substituted Zaitsev outcome, you do that with a small base. So at the top, we have here this tertiary alkyl halide reacting with ethoxide. Why not any substitution? It's tertiary. SN2 won't work. Why not SN1? Do you remember the talk about this, the conversation about this? Why will that not do an SN1? Because the base is so reactive, it won't allow the substrate to collapse. It will go after the substrate and make something happen. Okay? That basic condition right there, and understanding pH next term is absolutely crucial. This thing down here, the ethoxide, is so reactive, it won't allow this molecule to do anything it wants. It will go after it. It can't go after it in an SN2 sense because it's too crowded, but it can go after it either here on the left or here on the right. On the right, we get the Zaitsev. On the left, we get the Hofmann. Which of these two is more stable thermodynamically? The left. Why? More substituted. Why? What's the background to that? Why having more substituents on a molecule makes that more stable? Share of electron density, right? Those are electron donating alkyl groups that help stabilize sp2 carbon. So having more of them is better. Be careful here. Again, thinking about next year. This is the more stable product, but in this instance down here, we can get more of the less stable product. What that should tell you at this stage of your chemical lives is that this reaction isn't going backwards. This is a kinetically controlled process based on rates of reaction, based on steric environment. And once you get your products, you are stuck with your products. You are not equilibrating here. You're not going backwards. We did deal with that. So this is all based on steric environment. We can then mess around with the conditions by changing the shape or the size of the base and then affecting the outcome. So at the top, we get more of this more substituted product because this base here can get to the secondary hydrogens. You sense how stable the transition state is because you're making a double bond, your carbons are becoming sp2, and the alkyl groups help that. That's why it's a lower transition state. But down at the bottom, this stuff, for example, is very big. This is even bigger. This is Cottbus, and this is bigger Cottbus, right? And this thing here isn't messing about. It's got very little chance of getting into here. It's going to go for the primary positions, and you get that product. You can now use that. That's part of your toolbox to design products, to give products based on those simple ideas. We talked about stereochemistry quite a bit. We did some ideas where we could get cis or trans, if you like. The ideas here, basically, you're going to get more of the trans because it's more stable. And where do both of them come from? You can rotate around these bonds. You can have eliminations from different shapes. That gives you different outcomes. So we also talked about additions. Additions got very busy, and we had to worry about how to control these reactions. We did additions at low temperature, typically, because you want to avoid delta S being an issue. And then we started to think about this stuff. Markovnikov, bless you, okay? This thing is important. It dictates the regioselectivity of things like alkene additions. A whole bunch of them there. Some of them were concerted, some of them were stepwise. We did all the mechanisms apart from the addition of H2. The addition of H2 is here. That's the only one we didn't do. We did all of these other mechanisms. So go back and understand the fundamentals, recognize the reagents, and I think 12 is a nice time to do that. We've done that already in recitation. We've been looking at lots of reagents already. Go back and see what we can do there to add. To finish off the semester, we looked at alkynes. Alkynes are your best way right now of knitting carbons together. Next semester you'll have, I don't know, 12 more different reactions like this. Aldol reactions, you'll have Diels-Alder reactions, you'll have all sorts of new SN2s, all kinds of chemistry to make carbon-carbon bonds. So do well on this so that we're okay the next year. You can turn a terminal alkyne into an internal alkyne by alkylation. So on Monday, there is a page of synthesis. Make these molecules from these starter materials. That's what I'm looking for A's and B's. If you can get those things, you should be getting an A. If you're lost on those things, you're probably not going to get an A in the class. You really, you really need to be proving to me that you can handle this material at that stage. There are 3 questions with 3 different starter materials, 3 different products, and your job is to tell me how it works. Now read the questions carefully. If it says give me a product from each step, don't just give me the final product. Give me a product from each step. Right, Robbie? Yes, right? Just read the question carefully and you'll be happier. We finished off with radical chemistry. This was the end of the really important material where we spent time thinking about why some systems prefer radicals rather than carbocations or concerted processes. And the answer was because of the weak bonds. BR-BR bonds are weak, OO bonds are weak, and that's why they fragment. And again, we could list these steps. And one of the problems that you'll find on Monday is again recognizing which is which. Which does radicals, which does carbocations. And just a little piece of advice. If you recognize it as radicals and you're confident it's radicals, write down the word radical. Write it large on the piece of paper. And then check when you're finished to make sure that you had radicals, not carbocations. On this past quiz, I had way too many people start off with oh, this is radicals, great. And all of a sudden carbocations show up, blah, 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 blah. I want to text my friends, can't concentrate. Be careful. That's a problem next term. Be very careful. So those processes were logical, and we ended up doing sort of additions. We did radical halogenations. We put the halogens where we wanted them to, which is very useful because now you can dictate the outcome. If you want to make a tertiary alkyl halide from an alkene, you probably want to add HBr, because that's Markovnikov addition through carbocations. If you want to put the Br on the primary position, you've got to go through radicals because that's the outcome, okay, using the peroxides. So we did lots of synthesis. You all right? It's the kid in front of you I feel sorry for. He messed his hair up. Synthesis. We did lots of this as a sort of a review to look back and see why this is important. This is where we finished for the term. There's a question like this, no doubt. You've got 6, 7, 8, 9 steps. You need to give me the products in between. Now, you can get lost quite easily on these things, but you've got some help. You can start from the top and work your way down. You know where you need to go. Keep an eye on that product. Or you can start backwards. You know that the precursor for this, if you're making a transalkene, what was the precursor here? An alkyne. That's a clue. There's an alkyne. How do you make alkynes? Then it falls into place. I hope. You can work from both directions and hopefully get the answer or the answers as required. You're definitely going to see these. These are fun because they're little puzzles and an indication, if you can do this, you're set up for next term. If you can do this, you should get through the organic sequence first time round, and some of you will do really well at this. So with that in mind, on Monday, final exam here starts at 10:30, right? It's 2 hours, 200 points, a lot of possibilities here for grades to go up. They usually go up, unless you're just completely ignoring this stuff, they usually go up on the final. And so if you're sitting in a comfortable C, you could easily get a B. If you're sitting in a B, you could easily get an A. So put some time in over the weekend and let's see how that goes. Good luck with your finals. We're going to hand the quizzes back in a minute. Good luck with your finals. Good luck with whatever you do over the break. Be safe, be careful, come back in January, and enjoy the winter break.